So I'm going to go ahead and get everybody who's physically in here started on some Edpuzzle visualizations for 6.2b. They have already taken notes. I just didn't start the recorder earlier because they were getting some work time in. They've already taken notes on 6.2b to get started, so feel free to pause and take this page of notes. Then we went ahead and we went back to 6.2a with homework. There are only 3 questions in WebAssign, but they're a little rough. There's parts A's and B's and maybe even C's and D's. I have some hints up on the whiteboard in the room, but I also gave shout-outs real quick to gentlemen that were in here working yesterday with Hovan and Benny and Lucas and Josh Yang. Others can definitely probably provide support as well, especially after we got some work time done. But they worked a little bit on trying to work through their own, like where they were at in homework, and this slide was very helpful for number 1. But what I have them doing right now is transitioning. Not to that. That is not your guys' classroom. Here we go. Two new Edpuzzles that are due by the end of today, so get it done now. I want you to watch. I'll do the fun music because the music gets really weird and intense and dramatic, unless you want to listen to it on the videos. We can, but it's a little weird. I'll keep the fun music going, but I need you guys to wait. Watch 2 different videos, okay? There are 2 Edpuzzles. So get on in there, watch both Edpuzzles, mark them done. You have some nice free points just by getting some visualizations in for 6.2b. I need you to stop on the WebAssigns right now. Take a picture of the front board. I'm here to support you. But go watch these visualizations. They are about 2.5 minutes each. So I am going to pause the recording, put on a timer. It should be done at the end of 6 minutes. Notice, in some ways, it is so similar to what we were doing because we're using slices to get volumes, but the slices are very specialized because they are circular. And why are the slices all going to be circular in these shapes? Because that region is being what? What's that region doing? What happened in all of those different figures? Being what? Rotated, or more specifically, revolved around some axis of revolution. It's being spun, and as soon as you spin, what shape are you forming? Circular slices. If you cut it a certain way. If you cut it an awkward way, it might not be circular, but if you cut it... Wait a minute, help me out. Hey guys, how would you have to slice something like... can we call this like a solid vase? A hat? Wow. Yeah. You guys have a very special... Doesn't it look like one of those that you put in the middle of your table and then you put like a candle in the middle and there's some sand in there and it's like, okay, fine. Sand. You guys have obviously never decorated for weddings. Coming back. Okay, what else would you put in there? Rocks? Water? Oh, actually we have done the floating ones before. Oh, right. Anyway, what? Never mind, I don't want to know. Okay. What way do I have to cut this figure to have circular slices? How can you mathematically describe which way you slice this to get the circles?
A vertical slice.
A vertical slice. A vertical slice. So let's go from like top to bottom, right? As opposed to what other slicing could you do? Just to say like basic slicing, either down or across, right? Like across would be like a bagel unless you do it this way. Across versus down. Now, how math puts it, ready? How math puts it is going to be perpendicular. The slices are going to be perpendicular to the axis of revolution. Probably a good idea. Perpendicular to the axis of revolution. If you slice, we actually call it in like BC because there are other ways of slicing. We call it perpendicular because then it's like, oh, perpendicular, that's right, you're making discs, you're making circles. Perpendicular, some people say just to be able to remember. Thank you, sir. But that's like what Josh said about slicing down. But if this was oriented differently, I wouldn't be slicing down. If it was like on its bottom edge, I would be slicing across to get the circles. So it's better to say just perpendicular to the axis of revolution. And when you guys were looking at this in the videos, it was only showing x-axis, y-axis. But technically, we could be going around any horizontal line or any vertical line. We could do diagonal lines, but those are messy and they're really hard, and that's beyond what we're going to stress about. But when you slice it that way, don't you get circles. And not semicircles, full circles. P.S. Semicircles are a little bit rough in 6.2a, because when you go to plug into 1/2 pi r squared, if you notice, homework help, homework help, homework help, your top minus bottom is your diameter. So if your top minus bottom is your diameter, you actually have to cut your diameter in half to get your radius. In 6.2a, when you do the semicircles, blessings be upon you. When you do your semicircle, it gives you a picture, and in that picture, your top minus your bottom is your diameter. It takes extra work. But here, do you guys see the region underneath? Do you see the region, and do you see that the region, since it's being spun, the top minus bottom is the radius? The top minus bottom is the radius. So those of you that fully understood that semicircle example, we cannot cut it in half because it is the radius itself, which is what you see here and here. But this example, we call them discs. And discs are solid, aka no hollow. And it's formed when the region is flush against the axis. Now, I heard that some of us got this wrong when I was asking, so hold on. What does flush mean? Perfectly against, perfectly meeting, not one of those like rough constructions where it's like, yeah, I glued these together and there's like all these wobbles and it's not smooth and it hasn't been sanded properly. It's not perfectly interlocking or fitting. Lucas, do you have one of your pens? Where you have like, no, this one works. How did Lucas, these are different sections of wood, right? Cool. How did Lucas make it to where this is perfectly smooth and there are no gaps in between? Lucas, what did you do so that these different pieces of wood, I'm assuming, was it glue that got them all together?
Yeah.
But how is it so perfectly flush with each other, all the pieces? Mm-hmm. Right? Now, would this pen be near as snazzy if there were huge gaps as you tried to glue these and the angles were a little bit off? That would be a poor example of a pen, right? Like you could probably still write with it, maybe you could get it still together. But it took a lot of work to make those pieces flush with each other. The first year I've actually had something to show. Nice. What I mean by flush is that this region is totally against that axis because when I spin it, is there any hollow space? No. But in some of those pictures, wasn't there some hollow space sometimes? Right? And wasn't there times when those slices would have had huge gaps, huge air pockets, huge missing pieces in the middle? We would call those washers, not discs. The geometry is very similar in some ways, very different in others. You guys already watched visualizations. Let me not go through there. But let me instead see if you understand. I haven't solved them yet. But do you understand why this is a disc, why this is a disc, why this is a washer? Check them out. What's the difference between these two and that one when spun? I just need to see if you got the visualization from those videos. For which one? Yeah, number 2 is going to have a space. Why? Can you guys see all this hollow? That would be, right? It's not flush against. Does flush make sense? Where am I spinning it? This one I'm spinning it against X. It's flush against X. Perfect. There's not going to be any hollow space. I can use a disc, not a washer. This one, when I spin it around Y, these are arrows of rotation. This is the way to show it if you're showing work. Flush against. This one, not flush against. Cool? Okay, now we haven't talked about the math for this one yet. It actually is a bit more complicated, and you'll see why in a second. But let's do the math of these two, because we have the forever card that you guys hopefully already have written down. Okay? Volume equals, at the very top of the page, I can still use the idea from 6.1 that volume is equal to the integral of area from x1 to x2, or y1 to y2. I can still use that, except if we're in this section, things are being spun. So instead of using a general area, guys, what area formula can I use since they're all being spun? What's the area of a circle? More than pi, but you're on the right track. Pi r squared. So I'm going to use pi r squared. Except this one's going to be an r of y in terms of y, and this one's going to be an r of x in terms of x. And as some of you guys have noticed, this can get kind of messy with squaring, so just make sure that you're getting like the whole thing squared. And be careful, don't your calculators have like a forced parenthesis? If you're using your calculator, you have to have that squared inside the integral parenthesis. You can't go outside. But anyway, that's just calculator speak. Okay, now let me show you real fast the difference between a dx and a dy. All right? For this one, to get a circle, am I slicing down or am I slicing across for number 1? To get a circle. Huh? Okay, it's okay, it's okay, it's okay. Come back to the shape that you had a second ago. Come back to the shape. What slicing makes circles if the whole shape is drawn? The slices that are what? Perpendicular to the axis of revolution. So here's my axis. I slice down. Perpendicular, 90 degrees. I slice down if it's this way. If you notice over here, I slice down if it's a horizontal axis. I slice across if it's a vertical axis. Let me show you. So this one, I would slice down as just a representative. I would slice down, and then I would spin it. You see it? Not a perfect circle, but it's the idea. I would slice down, and then I would spin. And as I spin that little slice, I'm going to end up with my, you guys can think of it. As I slice down, I'll end up with my disc. Do you see it? But I'm going to slice across for this one. Still perpendicular to the axis. I'm going to slice across, then I'm going to spin that. And as I spin it, I'll get my disc that way. Why am I showing you this? This one's slicing down, this one's slicing across. Guys, as I slice down, I will be having a top and a bottom. As I slice across, I'm going to be having a right and a left. And why am I telling you this? I'm trying to make a connection. Our brain needs these connections to remember things. Top and bottom, right and left. Where are those coming from? What are these supposed to be telling your brain right now? Top and bottom in 6.1? Top and bottom was what? dx or dy? It was dx. Go look at your formulas in 6.1, because we shouldn't be on our computers, we should be on our notes because these topics are tricky. Oh my goodness! 6.1, if you were to look at your forever cards, top minus bottom, that is dx. Because I have a y equals f of x and a y equals g of x. Right minus left would be an x equals f of y and a x equals g of y. So if top minus bottom is a dx, I'm going to need to be putting this in a dx formula. The geometry tells me I need a pi and I need a squared, but because it's a disk, because it's flush, because I don't need to punch anything out, chisel anything out, sand anything out, cut anything out, I can just say something as simple as, ooh, top, who is that? Oh, this guy. Minus bottom, who is that? Well, that's boring, it's just y equals 0, because on top I have my 3 minus x square rooted. On bottom, I have my y equals 0. If they had given you words, they would also give you x equals -1 and x equals 3. Let me pause and check in. Let me pause and check in. Oh, guys, write it in your notes. You're killing me. Do you have the example written down? Why are you dealing with ripples? Has nothing to do with what we're doing. Yeah, come on. On top is that, do you see the y equals square root of 3 minus x? Yes. On bottom is the axis, which is the same thing as y equals 0. So the top y, that f of x. The bottom y, 0. Okay.
So let's
pi r squared.
let's say if you're given only one equation, do you just assume that the other one?
They better have given you more information than just one equation. Or they say something like and the axis, you can make it 0. They say and the axis, then
Plus you know where.
but it's not an assumption. I'm just going to where they... Remember in 6-1 where we were doing all the shading and we had to think of the boundary lines? Like, we're using those boundary lines. We're using the axis, which is 0, the curve, the x equals -1, and the x equals 3.
Steve,
Yeah.
what if the boundary wasn't?
Or if the boundary wasn't?
Yeah.
Let's say, well, there are a couple different ways that can happen. Here, let me show it over here. Solid question. I have other examples, but we can try to just condense them and show it here. What if it was the same region, but let's say they didn't say y equals 0. Let's say they said y equals 1. Then all of a sudden, the thing that I'm spinning isn't quite the same. Because if they were to make the boundary something different, what if they made it like y equals 1? But let's say we were still spinning around the x-axis. All of a sudden, this is going to be a washer. So I'd have to wait until we talk about washers to do that one. So I'll come back to that in a second. What if I had the same thing, but I had y equals 1 being spun around y equals 1. So it is flush. This one would be a disk because it's flush against whatever I'm spinning around, which is that y equals 1. I could go ahead and almost use the exact same thing because I'm still spinning. It is flush around this guy. So I would have my top minus bottom that's being spun like this. Just being spun a little bit higher. It would almost be the exact same thing. I would have my pi, I would have my squared. It is a top bottom, so it's dx. But I'd have to change a couple things. I could still use my square root of 3 minus x, but it wouldn't be minus 0 anymore. What's the bottom now since it's here? So it was this guy minus 0 when I was going all the way to the axis. If I stop it a little higher, then it's going to be my my square root, and then my y equals 1. So I'm going to have my minus 1. I think you're thinking of the circle where it's a positive square root, negative square root. I don't have another side to it. But then my bounds would be different, right, bud? Because I would have my negative 1, but wouldn't I need to find my intersection point? I'm just going to call it A for right now. So that would need to change. Or if I had something, well, I could also have y equaling like a negative 2, but it wouldn't be able to spin around the x-axis because that would be some weird shape, like that wouldn't be possible, like just physically possible. So if I was to have it go somewhere else, I would need to have like a different region, but I could do something like this minus a negative 2 just the same way I did minus 1. I'd just be subtracting a different y value. Let's see what's different with dy. Not much. I have my pi. I have my squared. Ew, I have my thin pen. Sorry, hold on. Give me a sec. Get it in a second. Pi r squared. I still have a circle, but I'm slicing across to get that circle, perpendicular to the axis. I'm slicing across. It's going to be a right minus left as I slice across. What's always on my right is going to be, but I can't put x's. I had to correct a couple of you guys a couple different times, people after school, people in class, because if it's a dy, don't I need functions in terms of y? So I would need to do things like y minus 3 is equal to negative 2x, and then divide everything by negative 2, so x is equal to negative 1/2 y plus 3 halves. I would need to get x by itself. Or if you want, I don't even have to make it look that gorgeous. That would be if I'm solving by hand. I could just do y minus 3 all over negative 2, which is the same thing as what I wrote. But who's on the right would be that negative 1/2 y plus 3 halves. who's on the left is going to be 0 because x equals 0 is this line. And then this guy is going to be my x equals, there we go. And then all I need is not x bounds, what do I need? Y bounds. And so how low do the y's go? 0. And how high do the y's go? 2. If I was solving by hand, I'd have to FOIL and use the power rule and plug and chug, but I'm not teaching you how to do integrals this section. I am just having you learn how to make the integrals that solve for the volume. These are 2 examples of discs. Quick debrief, quick check-in. 2 examples with discs. Pi r squared, either a top minus bottom dx or a right minus left dy. Shouldn't be too bad if you've been understanding 6.1, 6.2b. No, 6.2a. But what have we not done? I need to wait because we need to get, you guys have already seen some Edpuzzle visualizations. We need to get the idea. Okay? Now, you could be very artistic, or you could be very wordy, or you could be both. This is the idea of what needs to happen. A subtraction needs to happen, but a subtraction of 2 volumes. Oh, what happened to my poor little cone? Oh, that's so sad. His edge got screwed up. I'm carrying way more than I should. Give me a second. Let me just fix my cone. Poor little cone. It's not that big a deal. Okay. I need a subtraction to happen, but that subtraction has to be of the volumes. The subtraction has to be of the given dimension that I need. Like in old school, like, do you guys remember those tests that you used to take, like in middle school, or kind of like the PSAT, although we had COVID, so I don't even know what your experience is right now. But like those old tests, you would sit down and you would just like do the logic and the math and the reading comprehension and all that stuff. Well, now it's called Iowa testing, so we got new ones. Anyway, how could you find the area of like a house? How could you find the area of a house? We never memorized it, but you do know how to do like a triangle and a square, right? Or how could you find the area in between? Square minus circle, because the square is bigger. But square minus circle, right? So you would do like this is equal to 2r by 2r. So you could do the square, and then this is equal to pi r squared. So I could do 4r squared minus pi r squared, and that would be all the outside. But the point is, I'm doing an area plus an area minus an area if I'm trying to find area. Same thing with volume, except I need to do volumes minus volumes, or volumes plus volumes. And this makes the formula harder. Not a lot harder, but harder for your natural intuition. So let me get the forever card. I'm going to join it on one screen so that you guys can kind of get the information down like you did with discs. Oh, the spacing's off. Lame-o. You throw on one song, and during that song, try to get the key information. You can be as artistic as you want or as wordy as you want. Let me pause the recording and let you guys write it down. Where are we at? We were on 45 is discs, 46 is washers. Okay, I think we have 45 and 46. I think if my numbering is right. Okay, I need you to get this idea because it's where most kids make mistakes on the actual AP of easy problems where they say just write out what you would do. Write out the integral. There are always questions that say write but do not solve. And my kids, the nation's kids, make mistakes on washers because they don't get the idea. The idea is I need to do a volume of the whole outer shape. I need a volume, pi r squared. Pi, top minus bottom, or if it's right minus left, of the whole shape. I need a pi r squared of the outer minus a pi r squared of the inner. The subtraction does not happen inside the squareds. I have two different squareds. I have two different volumes. Benny.
For the capital R, does that mean the derivative?
Capital R is specifically talking about, ready? The outer radius. Put it here.
So it's not in the
Well, it's inside an integral. But the capital R is the outer radius, whereas the inner R, the little r, is the inner radius. I have two different radii. A washer that you would get from a hardware store, a spacer, whatever you want to call it, has an outer radius, the radius that would get to the outer edge, but it also has an inner radius, which would get to the inner edge. So then I could talk about this little guy like having his radius, which at the very edge is probably the same, but as you move in, that little radius gets smaller and smaller and smaller for the slices, whereas this one gets bigger and bigger and bigger. So what I was talking about for these ones is I have my big R being the top minus bottom of the whole thing, and I have my little r being the top minus bottom of the hollow or of the inside. So you can also think about it as an outer and an inner radii. Some people have done that and it's helpful. So I can also think of this as my outer and this as my inner. But I'm just doing two volumes and I'm subtracting. That's it. I'm doing two volumes and I'm subtracting. So over here, I could think about, if it helps, in your forever card, you might even want to put it, R is the outer radius, little r is the inner radius, and I still have things like, for the outer and for the inner, if I'm doing like top minus bottoms, then I'm still doing dx. And if I'm doing right minus left, I'm still doing dy. I haven't like rewritten the old stuff from the other cards. They're there, but I haven't made a huge deal about it because it's kind of like the same things keep on getting reiterated. But I have an outer and an inner. I have a whole and a hollow. I have a big piece and what's being subtracted or taken away. And this can lead us to going back and solving that washer problem. If I need to do a washer, which this guy has, my formula is going to be V is equal to, I can bring my pi out. I can, but on the inside, I need two different squares. I can bring my pi out, but I need two different squares because I'm dealing with two different volumes. The one that's staying, the outer edge, and the one that's being punched out, subtracted away. As I'm looking at my picture, if I'm slicing perpendicular, it's going to be a top and a bottom of my big R and a top and a bottom of my inner R. I'm just showing two representative ones. There's nothing to be like figuring out numbers for, etc. But I have my big R and I have my little r. Because it's top minus bottom, I know that it's going to be a dx. I know I'm going to be using my x bounds, which will be x equals 0 and x equals, I think, 1. I should probably do like an intersection to make sure that it's 0 and 1. Maybe I'll come back to that in just a second and think about if I set x equal to 2 minus x squared, maybe I should just do that now. It'd be x squared plus x minus 2 is equal to x plus 2, x minus 1 equals 0. My zeros will be at x equals positive 1 and negative 2. I don't want the negative 2, but I do need the positive 1 because I need that intersection point. I'm not looking at this intersection point, so forget that one. But I am using the 1. But my top minus bottom of my big R, of the outer R, is going to be that parabola. And in this case, it's going against or to this y equals 0. So I have my y equals 2 minus x squared minus 0. And Josh, if it was anything else, I could do minus 1, I could do minus negative 2, I could do any other line also. Just for this one, they had me go to the axis, Andy. They would say axis, and it's understood that's 0. Which doesn't end up making a difference, but I write it so that you guys understand it's top minus bottom. And my little r is separate. And my little r is going to be my y equals x minus 0. And then I would solve it. 2 separate volumes. Unlike the top minus bottom being curves maybe. In other examples, like area between would say parabola minus line. This is not doing parabola minus line. I need volume minus volume. So I need the parabolic volume, I need the linear volume, and I need to subtract. Hold on, I'm coming back, I'll take your question. Because I need this geometry, I need this dimension subtraction, volume subtraction to happen. Hold on, go ahead.
Couldn't you do, or could you do top minus bottom for the shade?
Absolutely not. I'm sorry, I just have to stop you and say absolutely not. And that is the very mistake that they're going to capitalize on and try to have kids get wrong. They don't try, it's just a natural intuition that's totally false. You said top minus bottom and absolutely not. Were you saying parabola and line? Weren't you saying parabola and line?
I'm saying with the axis.
Oh, so what I did. Sorry, yes, mine is right.
Okay, yeah, and then subtract. So whatever you do, and then subtract find the hollow space with the other. Like, do they both have to be top minus bottom, or could it be top minus bottom minus right minus left?
Oh, I
Like
see what
it's
you're
the
saying.
hollow thing you see.
Okay, but what I had to stop everyone else is hearing you say top bottom and thinking it was not like that. So, top minus bottom with parabola and line, absolutely not. What Havan is saying is, could one be x's and one be y's? Absolutely not. Why? I have to have them in terms of the same. So what you would be talking about is one rotation and another rotation at the same time. I'm not even sure what that figure would look like as to where the circles would be. I don't think they would be circles anymore. Because you would have like interlocking circles. You would have a whole other shape with whole other slices. Does that kind of make sense?
Okay, just because how did you, for subtracting the hollow region, how did you just do x minus 0? Don't you need a...
It's very similar to this shape in many ways. So what I did was my parabola, it was a parabola, not this weird funny shape, but it was a parabola all the way to the axis, which for me was around the axis. So I did parabola to 0, and then I did line to 0, which got me this shape minus that shape. Except our example that we were doing was around the x-axis, and so we had that 0 like right here in the middle. And so the line minus 0 got me the cone that needed to be punched on.
But isn't that not like count like parabolas? Isn't that just like...
The first thing I wrote, the pi big R squared, was the parabolic. So the first one got you the big pink one. And the second one's going to get you the blue one. So what you're going to get, sorry, I'm trying to use this picture, but just because it's the prettier picture. This is going to get me, what's it going to get me? It's going to get me this. My symmetry is not great. Like a bread bowl, actually does look a lot like a bread bowl, is going to be the parabolic one. Ooh, clam chowder, gumbo, what do you put in there? Ooh. Broccoli cheddar. Bread bowl, oh they do have the lobster bisque. And then this one is going to get me my...
They put in sauce. But that's in clam chowder too, yeah, you put chicken noodle, yeah.
I don't know, grad night, I usually go with like broccoli.
Just raw first.
Grad night, go to the sourdough bowl place. It's like a dance floor right there.
Oh, guys.
It's that guy, take away that guy, and I have what's the actual volume.
Just laugh at him. Don't worry.
Okay, so I'm asking if you can find the volume of the red part, and then like add
I
the
did.
number, get the whole number, like let's say it's 5, and then find the volume.
5 pi, hopefully, but yeah.
And then get the whole volume of the blue part separately,
Mhm.
like in a different integral or with a different dx.
Oh, you're just asking about integral properties. Yeah, the integral properties say I can take the integral of one minus the integral of the other. Yeah. But I'm just squashing it into one condensed integral because they're probably not going to show it as 2 separate ones. But when you solve it, you would integrate the first, integrate the second. The pi would go to both. So that's exactly what we're doing, Hovan, just I'm writing it in one single. According to properties of integration, that's literally what I'm doing. I'm just squashing it into one. And then factoring out a common pi. Does that make sense? Yeah. Yeah. But do you see how one's not going to be dx and one's dy? Like, I'm not going to have the orientation switch because otherwise I would be like having this somehow be circular and then this somehow be circular and then trying to think like a slice is, the orientation's off if I imagine something like that. Does that make sense? But yeah, I would be integrating it piece by piece. Okay. We already did that one, so I can just delete that page because we went back. And if you guys notice, I have some like, hey, CalcAB is helpful. Oh, that's right, I assigned CalcAB, and we have a very crooked homework. But then you have homework on 6.2, but it's not 6.2, 6.2, it's 6.2b, right? It's not just a normal 6.2, it's 6.2b. Let me try to make it a little bit more straight and a little bit less crooked. It might be like homework 37, I don't know. I've changed a few things the past couple years. But then we're at the end. Go ahead, Andy, let me get back to my formula.
Can you go back to the example you were
Oh, the washer one?
Yeah.
Yeah.
So you didn't use the negative 2 because you had the axis, right? For like y equals 0. And then you used the 1 because, okay.
Sorry, that got erased and I didn't mean for it to.
Okay, yeah.
So I did top bottom of the outer and then of the inner. Does that make sense? And in case it's helpful to see it this way, the top was the parabola and the bottom was the axis, which was y equals 0. This one, the top was the line and the bottom was the axis, which for this one was 0.
No, I'm saying for the bounds of the integral.
Oh, the bounds of the integrals, I used my 2 different x's that I had, which was x equals 0, started off the shape just in this picture, and x equals 1 was the intersection that I used that stopped it, that ended it. Does that make sense?
Yeah, that's what I'm saying. You didn't use the negative 2 because you didn't go.
Because it wasn't shaded. If it was shaded, I totally would have used the negative 2 to the 1. But my axis would have also needed to be different because I can't have this like rotating in on itself and actually be a solid. Like it would be this weird. A 3D printer could never do that. So we would stop this shape at the axis that we're revolving it about. And they didn't, they could have had us do this, but they didn't, so that's okay. So I just took what was shaded. Good question. I just took what was shaded. I would love to have another example handy. I don't have another example handy, just to be honest, because I assumed that would take all of our time. What we could do is I could just open up real fast because probably not too many people have gotten started on this one, even though I saw maybe a couple of you guys get into it. You're going to be watching a video and saying true or false, P.S. it's true, but please just watch it. I think it's helpful to see and to hear them talk about this formula of pi r squared, big R squared minus little r squared. And then they're going to have you walk through a step-by-step one. Can we just kind of think about discs or washers together? Is that okay? If this one tells me to revolve about the y-axis, which is this guy, guys, is this going to be a disc or a washer? Because it's flush perfectly against, right? Okay, what if I was to go down to this guy, and they tell me that I'm going again about the y-axis, who's he going to be? Watcher. Now, can I just help on this one? Is that okay? When I go to think of this, I'm going to need to slice across, which means I'm doing a dy. I'm going to be doing a right minus left of the big R, but then do you see how I'm also going to have to do a little r? Does that make sense? I have to the outermost edge and I have to the innermost edge. I would do things like get x by itself. You might want to take a picture of this unless you're in a rush. I have this and a negative square root, but if you guys look at your picture, I can ignore that because all I have is the positive square root. This guy is going to be x equals 4. So I'm going to have my big R squared being 4 minus 0 squared. My little r squared being this guy minus 0 squared. And I'm going to have from my bottom y to my top y, which I would need to find my intersection. The color coding isn't gorgeous, but that's exactly what you would need. Feel free to take a picture, then you guys can go ahead and get on here. Thank you so much for all the good work that you've put in, not just today, but all year, and we will try to put this all together on Thursday. Bye, guys.